I'm going to present a number of short lectures to reinforce or complement the Econ course that I'm teaching. And these lectures are on math, relatively simple math, algebra, calculus, and some statistics. This one is on the derivative. And the derivative is all about change. In other words, what is the change at a point on a graph, or if you're driving, what is your change? How fast are you going? Are you speeding up, slowing down? What is the change? And I might just say that in terms of economics, Armin Alshin, when he wrote University Economics along with William R. Allen, two of the most brilliant economists that I know of, certainly a lot better than some that have won Nobel Prizes, and I have no idea why they didn't win them, stated, you know, why do we make students take all these courses to get to the doctoral, the point of taking to writing their thesis? You know, they could write their thesis a lot earlier, but they took this rather rigorous boot camp type program. And he stated it was so, he said after their bachelor's degree they know all the economics we're going to teach, but they have to believe in marginalism, the application of everything being on the margin. So that being said, and those are the words of someone much greater than myself, I strongly recommend that here's an old book, University Economics. You can see it's been back in the 60s. It's the second edition of University Economics. I have the first edition up there too. Brilliant book by Armin Alshin and William Allen. And they later came down with a much smaller version, Exchange and Production, Competition, Coordination and Control. And I like to teach from this book. It's short, concise, and it fits in with a semester program or a year program at most. And some of the articles in here, which have been put into the book, the one on Fishland, etc., are extremely powerful. Anyway, having said that, let's realize the objective is to make math complement economics. I don't want math driving the economics. I want math to complement what we understand their economic principles and concepts, and framed in the orthodoxy of the discipline. Anyway, so what we're going to do is start and talk about slope and change. So the first thing is if we look at a graph, well, this axis is the y-axis, the vertical axis, and the x-axis. And in this axis, the x is positive and the y is positive. Now, if I added extended the x-axis over here, it would be minus. If I extended the y-axis down here, it would be minus. So you can see you could have a combination of minus y plus x plus y minus x minus x minus x. So the four quadrants, but I'm just going to give an example from the plus quadrant here today. I'll raise this and redo it. Didn't raise very well. So if we look at this quadrant with a y and x, all the points, the infinitesimal number of points, I mean the infinite number of points, nearly infinite, inside the space, can be denoted by using x comma y. So if this was 5 on this axis and here was 5, then we would write at this point 5.5 x, y. If we took this point, 3 and 5, we would write x 5.3. And if we wanted to, if we just had these 2 points, and we could do this for many points, we could join them together and put a line through them. And that would be a straight line. And we know the slope, and we know the coordinates at the start and the end. That's just a very limited example. So we note the slope of the line as slope equals change in y over change in x. So we know this slope is consistent, but you could have a slope like this, which would go through a whole lot of different points and would probably be described by a exponential function, but we want to know what the slope of this function would be. But the slope changes at every single point. So we need to develop a point to describe it. Now, if we go from this point to this point on this curve, we know that this is change in y, and this is change in x. So that gives us an average slope between these 2 points. It was average slope. But we really are interested in the slope at a point. But one of the problems of doing things as a point doesn't really exist. I mean, it doesn't have any dimension. It's like here's the point here, and there are a zillion numbers. Say this is 6, and there's 5.9999 up to that, and then there's immediately you get there. There's 6.0001 goes out till you get to 6.9999, and then you get to 7. So there are all these points in between, and we can show that there is a definite change that allows you to go from 6 multiple 9s to 7 and so forth. That's for a later lecture. But I just wanted to point out that points, they're without dimensions, but we use them all the time. So having said that, we're trying to approximate with very, very small changes the change at a point. And so we have to think about, if we get, sorry about this, but I've been using it too much today, practicing this, see how it worked. We need to get a small change on a curve. So if we have here this curve, we want to know what the change is right at that point. Well, the way we do that is we look at as the change in x, this is x, change in x goes to 0, but not quite 0, goes to 0, but not quite 0, like we discussed up here. Some infinitesimally small number, how that affects the change in y. In other words, the slope, delta y over delta x. We want to get this angle. this could be a cost function, for example. And if you had a cost function, you might want to know what the marginal cost was of producing this output. Now, we haven't got there yet, but everything we do with calculus in this class, we're going to try and go back and relate it to an economic principle. And your textbooks will describe this better. And plus, if you go online to Khan Academy and places like that, there are much better explanations of these mathematical concepts than here. But I just want to keep this concept of my class, what I'm going to do. So now we want to get to that small change, which is called a derivative, derived from derivative. So before doing that, we know that y equals x. Y is the dependent variable. As x changes, it affects y. So if y equals x squared, then we can write a schedule down here. Y and x squared. And x, we could just change x 1, 2, 3, 4, 5, 6. So we know that where y, and over here we can say x squared. So if y is 1, oh, I didn't do that right. If x is 1 and y equals x squared, then y equals 1. But for x, if x is 2, then 2 times 2 squared is 4. So y is 4. If y is 3, but the relationship is y to x is x squared, then y is 9, and so forth. 16, 25, 36. So this is what x is, but you have to square x to get 4. It could be a lot more complex than that, or simple than that, but probably not much simpler. But now we have an interesting concept in math where we basically say y equals f of x. Now I mean, it's the same thing, but it just says y is a function of what x is. So they write the equation in f of x equals x. And whatever x might be, x squared, which we've got here, could be x squared, x cubed, or it could be a longer equation. So if you see this denoted like saying f of x equals x or x squared or x free, it really is the same as y. I was a little confused by that when I first got going on this, because I was used to saying y is a dependent variable of f of x, but you've got to start learning to use that type of knowledge in your discussions. Here we go again. So we're now going to try and wind this lecture up. I will improve this system quickly. No, but not today. So we want to look at, we want to find the derivative, find the derivative. So now we're going to find the derivative of the slope of the function. So we know the slope equals change in y over change in x. And to find so we want to find the derivative of y equals f of x. So we know that delta y equals f of x plus delta x minus f of x. And we know delta x is delta x. This just simply says this is where we get to after delta x, but to find out what delta y is, we have to subtract where we started from. So this total, this amount minus this gives us the delta y. And we've got delta x because it's on the x-axis. And that's the independent variable in a sense that's driving it. Okay, so now we want to find, and our f of x, we've decided is x squared. Could be anything, x cubed, any other equation, but we're doing that. So we know that f of x equals x squared. So we know f of x plus delta x squared equals x plus, wait a minute, we take this out, equals x plus, sorry, equals x plus delta x squared. I mean, that comes from the fact that f of x is equal to x squared. These mistakes are easy to make when you're doing this ad hoc off the board. So let us expand this equation. X plus delta x squared, and that equals x squared plus 2 delta x plus delta x squared. And now that we've expanded that, now we have to take away from the delta x, because that's where we originally got to. So we take away x squared. I'm sure I got that right. And of course, this is changing y over changing x, because that. So let's do some simple crossing out here. So that crosses out, and that turns this into 2x plus, and that takes away an x plus delta x, and as delta x goes to 0, as this goes to 0, (2x) equals the derivative, which is what we're after. We get 2x. So the result of the derivative of x squared and we know that by the simple rules, but it's worthwhile going through this and also having a more complex equation there. But we won't deal with much more complexity than that in this course. Anyway, I hope that helps. Get back to me.